Hello dear students. Today let us derive the energy equation from the law of conservation of energy. Okay, yes. The law of conservation of energy states that uh, the energy can neither be created nor be destroyed. Okay, now for that we need total energy. So total energy here we are going to take kinetic energy and the internal energy. Okay, yes. Now, let us take a volume V of set of material particles at time t. What is kinetic energy of the material body with the velocity v, density rho, and volume v is nothing but what is kinetic energy? Kinetic energy is nothing but half mv square, right? So we have volume integral rho v square is nothing but v square dv. Let us call it as equation 1. Then we have the internal energy E of a material body is expressed as E is equal to volume integral rho epsilon dV, where this epsilon is the internal energy per unit mass, or it is also called the specific internal energy. Okay, so this is our kinetic energy and the internal energy. Okay, so this half is missing in equation 1. K is half into mv square, no? So that half is missing in equation 1. Half, let me write that half. So that half. Okay, so now we need the work done, the rate of work done, the rate of work done. The done word is missing here. So let me write the work done or power P. Work done, the rate of work done is also called power, right? By the external forces acting on the material body is, let us call it as P equal to, remember we are taking two types of forces, one is body force and the surface force. So we have the body force OB and the surface force S, and the rate of work done or the power is nothing but dot velocity, dot product velocity. Similarly, the surface force dot product velocity, and here it is the volume integral and here it is the surface. Let us call that as equation 3. This is the rate of work done or the power, that is by equation 3. So what is our equation 1? Equation 1 is kinetic energy, equation 2 is internal energy, and on the RHS I want the rate of work done or the power, so take that is represented by equation 3. Then we are dealing with energy, so let us take this, the amount of heat Q flowing out of the volume V, flowing out, that is going outside this volume. Let us call it as Q, right? Q is nothing but the surface integral. So how is the heat going? It is going across the surface S, per unit time. So Q is nothing but the surface integral, very, very important, surface integral Q dot N ds, where Q is the heat flux across the surface S. That is, let us call it as equation 4. So equation 4 is nothing but the amount of heat that is going outside the volume V. Then the heat generated within the volume, the heat generated within the volume per unit time, let us call it as H. So H is equal to volume integral rho H dV. Rho is density, of course, and H is the strength of the internal heat source or heat supply. In other words, heat source or heat supply. Okay, let us call it as equation 5. That is our equation 5. So what is equation 4? Equation 4 is representing the heat flowing outside the volume, and equation 5, it is generated within the volume integral, and equation 4 is surface integral. And the law of conservation of energy states that energy can neither be created nor be destroyed. Or in other words, the material time rate of change of total energy of a material body is equal to the sum of the rate of work done by the external forces and the amount of heat contained within the volume V. This law is also called the first law of thermodynamics. Okay. So remember, what is the total energy we have taken? We have taken kinetic energy and internal energy, right? So the material time rate of internal total, rate of change of total energy. So we have d by dt of K plus E on the LHS on the RHS is equal to what? The rate of work done, right? And the amount of heat contained in the volume, right? H and minus Q. Why it is minus for Q? Because Q is nothing but the heat, it is flowing out of the volume. The heat going out of the volume, so it is minus for Q. Let us call it as equation 6. The next step, we are going to substitute for K, E, P, H and Q in this. Okay. So what is our K? Our K is nothing but half volume integral, okay, rho V dot V dV plus E there, okay. On the RHS we have P, we have the volume integral and the surface integral, plus we have H minus Q. Fine. Okay. So just watch this equation. We have two surface integrals on the RHS. This is our RHS. On the RHS, we have two surface integrals. And we should remember to convert these surface integrals to volume integrals. Okay. Now using Reynolds transport formula for the LHS. Now let us take the LHS. This is our LHS. So d by dt rho half V dot V plus that epsilon dV. This is our LHS. This is LHS here. LHS. So by using Reynolds transport formula, what is happening? This d by dt will go inside. D by dt will go inside. Okay. So rho outside. So d by dt half V dot V plus E or epsilon dV, right, equal to whatever the RHS. RHS remains as it is. Let us call it as equation 7. Now, we have, remember on the RHS, we have two surface integrals. We have to convert them into volume integrals. Now, using Cauchy's law, right, S is nothing but T transpose N, where T is symmetric, using the law of conservation of angular momentum. So, we get S is equal to T N. S is equal to T N. So, now, let us consider the first surface integral on the RHS. Consider the surface integral. So S surface integral S dot V, right, ds equal to, so S we are substituting, our S is nothing but T N dot V ds. Okay. So now here what we, this is equal to N, right. We have this T N dot V is nothing but N dot TV. So using relation over there, right? Then that is equal to same surface integral dot product, right? Dot product is commutative, right? First I can write down TV dot N dot TV. I can write it as TV dot N ds. Okay. Now converting this to volume integral. So using which theorem? Using Gauss divergence theorem, right? So we get what? That is equal to, we get volume integral. We get the volume integral. So this has to be the volume integral. So divergence dV dV. Right. So what was our LHS? LHS was this. That is equal to, I have divergence of dV. No. Now using the identity now. So V outside dot, right, div T plus T dot gradient V, using the identity, that is splitting this, right, splitting this, we are getting this equation 8. So this is one of the surface integrals on the LHS. Similarly, there is one more surface integral, so we'll take that also, that is surface integral Q dot NDS, and this directly we can apply Gauss divergence theorem, and we get volume integral divergence Q dV. That is called as equation. Now using these two, 8 and 9 on the RHS, now on the RHS all are now volume integrals using these two. Now we'll substitute, right? So we have on the RHS, we have LHS is this, LHS is this, right? On the RHS we have first term is this. This was the one, the first surface integral converted into volume integral. This was H, and this was converted, right? So we have this. That implies now on the LHS we have this d by dt of v dot v. This is nothing but twice v dot dv by dt, twice. The twice and this 2 here will get cancelled, right? So we get rho v dot dv by dt plus that rho is multiplied here, so we get rho d e epsilon by dt dv. On the RHS, all the terms remain the same. This, and this. Okay, all the volume integrals now. Now the next step, what are we going to do is, we have let me take the highlighter here. So we have v dot dv by dt. We have all the dot products with v. I'm taking. So b rho b dot v, and then we have divergence t dot v. Then that's all, no? Yeah, that's all. So all the dot products with v, I'm taking it to the one side, right? So let me take the next step. So we have volume integral. Okay. So v dot product, all dot products with v. So the dot is missing here. So v dot the remaining is nothing but this rho dv from the first term here, that is this one, right? Then we have dot product v outside, so we have minus. Why minus? Because that minus rho b is coming this side. Okay. Then minus divergence t. Why this minus here? Because this was on the other side of the equality, so this minus. The remaining as it is. Remaining is, volume integral rho d epsilon by dt dv equal to the remaining, that is this, and this, as it is on the RHS. Now, why we took all the dot products together? Because we can see this as, this whole thing will become 0. This is by the Cauchy's equation of motion. By Cauchy's equation of motion, this part will become 0. Now what is remaining is, this much. So let us take all of them to the one side with one volume integral, all of them within one bracket, equal to 0. Now since v is arbitrary, the integrand has to be equal to 0. The integrand is this. And in the next step, we have taken this gradient v as d. Right. So take all the minus things. I mean, all these only this on the LHS, the remaining on the other side. That is called as equation 10. And this is the law of conservation of energy. And this is also called heat equation. This is also called energy. Right. This is the derivation of the energy equation. Okay, guys. So let's stop now. The next class, let us take up the problems on energy.